And now, as we have found the AX, AY and AZ components here, now it is time to find out the R cube components. So now look here to the R cube components. So here, let me do it here. What about R cube? Here is R. So what about R cube here? This is equal to, if I find R square, for example, first, because it will be easy to find. You will see in a while why I'm saying this. So we have the whole square of this, the whole square of this, and the whole square of this. So here we have x minus s prime cos phi prime whole square plus s prime and sine phi prime, this is minus m squared, and plus z minus z prime whole squared. Now look here, this will become x squared, and here it will be s prime square cos square phi prime. This will be s prime square sine square phi prime. So these two, this one plus this and this will become s prime square, and cos square phi prime plus sine square phi prime will come out to be 1. Sine square x plus cos square x equal 1. So we will have x square and we will have s prime square from here. Then minus 2xs and cos phi will be here, and from here we will have z minus z prime whole square. So I can write that this thing is equal to x squared plus s prime square plus z minus z prime square and minus 2x and s prime and cos of phi prime. So this is, so I can see from here that r square is depending on cos phi here, because our integration, when I will look at this d tau prime, and d tau prime is equal to s prime and ds s prime d phi prime and dz here and prime with this as well. So d tau is here. So we are having integration on ds prime, d phi and dz here. If we look here, these are all square functions. Square functions, so we have them as even function. Here, this cos phi dependence will make a difference, as it depends on cos phi, and if I even cube this one, then it means that r cube is an even function. So this implies that r square is an even function and r cube is an even function, part of that even function. And now look here, even going into the integration, what we will get basically here. So starting from this solid generalized form, I can write that now here the bi here, like the bi, so it can be bx, by and bz dependent on ax, ay, az as I cross r components. So bi is equal to mu naught I over 4 pi, and here this is AI, over R cube, and S prime, ds prime, d phi prime, and dz prime. So if I write x here, x will come in here, y and z. So this integration will be like this. Now first look at the bx component. Like what will be bs component? Here it will come out to be ax. And ax here is depending on sine phi. Sine phi is an odd function, while r cube we determined this is an even function. So here is the issue of odd and even function, whatever the other things are. But inside this integral is these are multipliers to each other. So it means that if one of the integral goes here to 0, then it means in multiplication all will come out to be 0. So ax here is basically the odd function, and this is even function, and odd and even are making the integral from 0 to 2 pi limit, symmetric limit here, and this will make our bx equal to 0. And when bx is equal to 0, it means our radial contribution is 0. And now we see the z contribution, which is the axial contribution of this toroid, means the contribution of the current component which is contributing to the magnetic field. So I've come to BZ component here, and we see that it is already sine phi and cos phi combination, odd and even combination in the even limits here. So it means this will also go to 0. We even don't think of RQ, although that is even, but here the odd and even combination is here, so it means the axial contribution of the current, this means like it's going here. So the axial contribution of this current to the magnetic field is coming out to be 0. So the axial magnetic contribution is 0 to the net magnetic field. And what about B and the Y component of this? So look here. In the y component, we see that it is cos phi, even function, and here the RQ is an even function. So it means this will not be equal to 0. It's an even function, so it will not be equal to 0, and it means that By, what is By actually? The By here, if I'm at x0, z here, means at observation point here, I'm observing the things at x0, z here, so y is 0. So along this xz plane, if I do rotate this thing along, then it means that the component which is at the point here is basically the direction that comes out, the phi unit vector comes out to be along the y unit vector here. And that's the only contribution that we have at x0, z here. So this gives us the means we are at a decision point that B8R at observation point is basically the value of B, the value of this B is only 8 phi unit vector. like B is this one. This is the net magnetic field. This is along the azimuthal direction here, is it was along the solenoid axis. But now here for a toroid, this is the azimuthal, and the axis of a toroid is the z direction. So we got the value. The magnetic field is basically only azimuthal one. And now our calculation is easier, that we can find, we can now apply the Ampere's law to this toroid in order to find out the magnetic field in three regions. There is one region, the one region is when this R is less than R1, like we are inside toroid. The R which is greater than, which is less than, are greater than R2, means we are outside of the toroid, and when R is such that it is in between R2, less than R2, and greater than R1. So it is inside the toroid here. We are going to find out the field in these three regions using the Ampere's law. And here, let's say the very first one is the inside the toroid case. So the first case, let me write the first case here. So this is, let's say, case 1, and case 1 is inside toroid. Inside toroid. So what will be a condition on inside toroid for this? R will be less than R1. The internal radius, R will be less than this one. Now for this one, circle of radius, we will make a circle impedance loop of R which will be less than R1, and the field, we know that it is circumferential here. The length element will be R, d, phi, and phi. So we have the Ampere's law for this, that B dot d L equals mu naught I enclosed. Mu naught and I enclosed. So we have the, from here, the B dot dl will make is P times, and dl around the loop 2 pi r. So 2 pi r here, and this is this will be B of r with us, and this is B of r and 2 pi r. And what about this? Mu naught times. Now how much current is enclosed when we are a distance less than R1? So we are not reaching the toroid. It means loop is somewhere here, and this is enclosing no current, and we have inside the toroid the magnetic field equal to 0. So V of R is 0 here. And when I consider the case 2, and that is inside the toroid, and then this one within the winding. So because here inside the toroid doesn't mean we are here inside, but we are here because toroid inside is this one. I have stopped it here just to show it like a 3D, although my figure is not that good, but to show it is 3D. So here, when within, this is basically within the winding. So within the winding, R is between R2 less than this one, greater than R1. So this is a situation where we are inside the winding. We will apply again the the Ampere's law. So the law will imply that B of R is here 2 pi R, and what about here, mu naught times. Now, how much current the loop then will enclose here when we are in this region? So it will be enclosing I current multiplied with the number of turns this loop is enclosing. So we are having mu naught times Ni here. And this will give us the magnetic field equal to mu naught Ni. B of R is equal to mu naught Ni and 2 pi R. And this is in the phi unit vector. And what about the third case? The third case is almost like the first case. The third case is when we are outside the toroid. Outside the toroid. So look here. This is outside the toroid, so R is greater than R2. We are outside the toroid. So B dot dl, B of 2 pi R, a mu naught, and the enclosed current outside the toroid, there is no current. So it means that is 0 as well. So we have the B of R outside the toroid also equal to 0. Now, one thing, we don't have any contribution of this current to the magnetic field in the axial direction, in the radial direction, and we have only this thing in the azimuthal direction. The magnetic field is in the center of this coil, and this is along the azimuthal direction here. Now there is something very interesting here that compared to the solenoid field was mu naught Ni. But this field, the magnetic field of a toroid, is basically 1 over R dependent. So it means as we increase R, the magnetic field will die down. You move the observation point away from this toroid and the magnetic field will be decreasing is 1 over R, which is one of the main difference between a solenoid and a toroid. In a solenoid, we were having a constant field inside, and here we don't have a constant field, but inversely proportional linear form. This is not nonlinear, only 1 over R. This magnetic field is varying. Now one thing, what if the solenoid is not circular like this, like if it's a square or it's a rectangular shape, the result will be the same. The reason, because whether it's a circular shape here or any other shape, then it is symmetric on both sides. So the symmetry is basically cancelling the shape of this toroid. We will have to keep this one thing in mind. And I hope with this, although we didn't do all the mathematical calculations, but from just the values we got, that which of the integral will give us 0 and which of the integral will survive. So I hope we have done this example algebra, complex mathematics, a lot of geometry involves, but the concept is clear that only the azimuthal field will survive. No radial contribution, no axial contribution.